Okay. That way now. No, okay.
Great. So, welcome everybody to the AI initiative colloquium, which is today going to be given by Yao Yao from the University of Iowa. And the topic is going to be optimization for fairness-aware machine learning.
Yeah, thank you.
Thanks for inviting. Can I start?
Sure.
Thanks for inviting. It's my pleasure to give a talk here. And today my talk is about optimization for fairness-aware machine learning. So as we all know, machine learning and AI systems have been used widely in high-stakes decision-making. For example, the bank can use machine learning to predict the loan default probability and use the results to make lending decisions. And similarly, we can use machine learning and AI systems for criminal sentencing and decide the insurance premium. Also, the machine learning will affect the resource allocation. However, as machine learning becomes more and more popular, some
I'm not able to hear, right? They say, can you unmute there? There's a
Oh, you have to
non-hearing.
unmute. For the Zoom, you need to unmute yourself.
but I unmute. Yeah, I unmute.
Okay.
So
good.
they should they can
No,
help.
no, it's just the Microsoft is mute, right?
But it's
That's the bottom corner. You have to unmute.
That is me.
yeah, that is.
Oh,
Okay, that's fine. Continue. It's okay.
Okay.
Yeah, sorry.
It's fine.
Very
Oh, now it's good. Yeah.
Okay.
Mhm.
So as machine learning becomes more and more popular, some concerns also arise with it. So for example, the COMPAS system, it has been widely used around the country to predict the criminal defendant's likelihood to recidivate. However, after 2-year follow-up on about 7,000 people predicted, researchers found that this system wrongly predicts Black defendants as future criminals twice often as white defendants. So obviously it's a biased and unfair system. So I would like to deal with this problem. How to avoid the AI systems that make discriminatory decisions for protected groups. Here, the protected group can be defined by gender, race, and etc. For example, in the previous COMPAS example, the protected group should be the Black, and the unprotected group is a white. So my methods include proposing threshold agnostic fairness metrics and developing efficient training algorithms based on constraint optimization. So let's first look at the the most common and the simple supervised learning, the binary classification. So we want to predict the label zeta, it can be 1 or -1 based on the feature vector Xi, and we have sensitive variable S. It can be protected group and unprotected group. And Z equals Xi zeta S is a random data point. Here we have the predictive model H sub X with X the model parameters. The decision rule for the binary classification is that for each data point, the predictive model can return a score for it. And this score is only one-dimensional, and we have a user-defined threshold tau. So if the score is greater than the tau, we predict this data as positive, and otherwise we predict it as negative. Okay, so how to measure the fairness of the model? So suppose we have the sensitive variable. It can be gender, age, and race. So fairness is essentially about how the score depends on the sensitive variable S. And here for the classification task, a variety of fairness metrics have been studied, including demographic parity and equal opportunity. So we can see that the demographic parity require the equal predicted positive rate for the protected group and unprotected group. And the equal opportunity requires the equal true positive rate for different sensitive groups. However, look at their formulation, we need to know the prediction zeta hat, which means that we need to know the threshold tau. So this kind of fairness metrics are called threshold dependent. However, if we use threshold dependent as the fairness metrics, we may encounter some problem. So first is how should we choose the threshold tau? A good threshold is not always easy to choose. So even if we can find we can choose a threshold tau such that the model is fair, it's likely that a model satisfied the fairness criterion on the one threshold, but violates the same fairness criterion under another threshold. Let's look at this example. So let's look at the graph on the right. We first rank the score from the high to low, and the blue dots represent the protected group. The red dots represent the unprotected group. We have two thresholds, tau and tau prime. And we can first look at the first conditional probability. We just need to say among all the blue points, how many of them are above the above the tau. So the first conditional probability is 3/4. And similarly, we can compute other conditional probability. So we can observe that the demographic parity is satisfied with the threshold tau, but it's violated, it's satisfied with the threshold tau prime, but it's violated with the threshold tau. So which means that we need to train the model again if the threshold tau changes. So to deal with this problem, we propose some fairness metrics based on the statistical distance, which means the distance between the distribution. We can look at the graph on the left. So it plots the density curve for the score of the two sensitive group. The blue is the protected group. The red curve is the unprotected group. So we can see that these two curves are quite different. So we call this model unfair. And if we look at the graph on the right, we can see that the distribution are quite similar. So we will call this model fair. And this kind of fairness metric are threshold agnostic, or we can call it a threshold dependent, because we don't need to worry about the threshold tau. And so we don't need to tune the tau. And also, actually, this is stronger than some existing fairness metrics. For example, if we look at the graph on the right, if the two curves overlap completely, the shaded area represents the predicted positive rate. And if they overlap completely, it can imply that the demographic parity satisfied.
So in this one, the reason your system gave you the wrong results because what you did not have enough samples for the protected group. What was the reason that you know that you say it's not fair, right? What's the root cause of that?
No, it's not because of the number of the samples. It's just because I mean the model is not fair. I mean,
and why model is not fair?
The output of the model is not fair for protected group and unprotected
And
group.
what's the reason for that?
What's the reason for that?
Because it's a data driven, right? You give a data, we train the network, and so why is it not fair? What's the reason, main cause of it?
I think maybe because the model used the sensitive variable to do the prediction. So like it's some kind of, so we want the model to be independent of the sensitive variable. However,
what is the sensitive variable?
Sensitive variable is it can be defined by the gender, age, or race. It's a feature, the data feature. one of the
Yes,
data
so
feature.
bottom line is, see, you have the samples and you
Mhm.
just train a classifier, but it's a very simple problem, right?
Yeah,
So what is it that it's, only reason is maybe you don't have enough samples for that protected group? I mean, I don't see any other reason. Like you were showing me.
so for example, actually in this, for this, campus system,
Uh-huh.
actually, we can see that it's not fair, right? Because it's
Yeah,
wrongly
sure.
predict the black. However, but we have more black data than the white data.
Yeah, but so explain to me, like, see, that's very simple, right? You teach a classifier,
Uh-huh.
which is,
Mm.
plain binary classifier, depend on samples, so there must be some reason to explain. Why is it
Mm.
happening? Like, can you go to the next slide? Like you were saying distributions? Go to the next one? Yeah,
Yeah.
here.
This
So what
one?
are these distributions? There are two distributions, right?
Yeah, we,
So-
yeah, these
So they
are.
are different for the protected compared to.
Mhm.
So then you take the joint distribution and you train a classifier, right? You take all the samples from both groups, is it right?
We didn't like,
So then-
it's already after we got the model, we predicted them.
Oh, there's a prediction. process.
It's a
Okay.
prediction, yeah, it's the
Okay.
output of the model, it's
Yeah,
already after.
So if you are going to do the actual, when the model you train on some distribution, some data, right?
Yes,
So in that, if you come up with these kind of distribution.
yeah, this is a result, I mean, the
It's the
output.
output.
Yeah, it's an output,
So what will be the input? Like you have the data set,
yes,
you train your network on that, right?
Yes,
Binary
yeah.
classifier.
yes,
So now, is there a problem there that you have less samples from
No.
protected group?
no.
They're equal.
We cannot say equal, but we just use the data, but like it doesn't mean that for the unprotected group has less, I mean, data points than the protected
Yeah,
group.
that's what I'm saying. They have less data point.
No,
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 it's not.
it's not, yeah.
So then what's the reason? Because it's a science, right? I mean,
Yeah.
you should be able to explain. it. Of course, it's a very good issue to resolve that. But
Yeah.
you need to go to bottom of that, right? So, okay, you can continue.
Okay, yeah, it's a good point, and, okay. Okay, so how to obtain the fair models? The three main approaches that can obtain fair models include pre-processing, post-processing, and the in-processing method. Pre-processing reduces the bias by resampling and balance the training data set. And the post-processing adjusts the prediction results after achieving the model to ensure fairness. And the methods in this talk are in-processing method, which enforce the fairness by adding the constraints or regularization to the optimization problem. So here, we prefer in-processing method because the pre-processing and the post-processing are heuristic methods with no theoretical guarantees. And the in-processing method can achieve a better trade-off between the performance and the fairness, and it can have the theoretical guarantees. So my work formulated the problem, formulates the problem as an optimization problem such that the performance of a model is optimized such that the fairness constraints are satisfied. So, however, the formulation, the implementation of the methods may encounter some challenges. The first is the fairness matrix will result in non-convex and non-smooth structure. And also the formulation is like most of the time in high dimensional space, especially when training deep neural networks and involving large data set. For example, the image data set, which can result in long training time. So let's first look at, for the binary classification, we develop a new fairness metric, which is AUC-based fairness metric. So before I talk about the fairness metric, let's first look at what is AUC. So the graph on the right is several ROC curves. The ROC curve plots the true positive rate against the false positive rate. And the area under the ROC curve is AUC. So we want, if we use the AUC as a performance metric, we want the AUC to be as large as possible. So if the curve can go through this 0, 1 point, it means that this classifier is a perfect classifier. And if it is this red dashed line, which means that it's totally it's a totally random classifier. So put it in formula, we suppose we have two samples, Z and Z prime. And AUC is defined as the probability of the score of the positive data ranks higher than the score of the negative data. Okay. So actually AUC is better for imbalanced data set. Because it's about just about the ranking. So it's good for imbalanced data set. And so we propose the AUC-based fairness metric. It's a new fairness metric, and it's called group AUC fairness, which is defined as the score of the data from protected group has half a chance to rank higher than the score of the data from unprotected group.
Just to be
Yeah.
So here the imbalance is defined with respect to this score probabilities or with respect to the data distribution?
The imbalance means that, for example, the number of points for protected for the positive group and the negative group are like very different. For example, for the medical data set, we only have a few like data points that predict positive, but we have like many like negative data. So because
it's
only
data, it's a data.
it's a data, it's about the data.
Yeah.
Yeah.
Good.
So okay.
And one more quick question. So this AUC based metric has been done before, like how to maximize the AUC area to talk about the performance. So how is it different?
Yeah, because if you use AUC for the performance metric, you want the AUC to be as large as possible. But it's different for the fairness. And as you say,
Okay, so you are doing it for the fairness.
yes,
I
yes,
see. Okay,
yes,
okay.
yes.
Okay, thank you.
Yes, thank you. So in simple words, this fairness means that if we use this score, the output of the model to predict the sensitive group, we want it to be totally random. So after you have the model and you want to use the output of the model to predict the sensitive variable, we want that it to be inaccurate. Okay.
So you put a constraint, right?
Yes.
When you maximize performance.
Yes.
So how that's gonna affect, say, the performance without constraint? So basically you're comparing two methods, with constraint and without constraint. So if you get rid of the, don't worry about the bias, any bias, and then just look at performance.
Yeah.
On prediction.
Yes.
Will you have better prediction in that case?
What do you mean, like a better
Say
prediction?
you go back to
You
the
mean-
previous slides.
So,
Like,
so
get
basically,
rid
the
of
question in the numerical section, do you have a comparison, compare the training result with or without
Yeah,
the
get rid
constraint?
of the constraint.
Yes,
right?
yes,
Will you get better performance.
yes, I will talk about it later.
Good.
We'll show you that. Okay, so it becomes a constraint optimization. We want to maximize the AUC subject to the fairness metric is satisfied. Okay. However, here the equality constraint is maybe too restricted because an absolutely fair model may have a poor prediction performance, and also it may be unnecessarily overly fair for the users. So we predict some flexibility for the users. We introduce the targeted level of fairness denoted by delta. So here delta is greater than or equal to 0, and we replace the equality constraint with two inequalities.
What's the difference between these two? I think.
So
No, I mean, the bottom two inequality things. I
so it has a flip sign.
Oh, yeah, I didn't know
Flip
this.
sign here, yeah.
I will-
Okay, so, and according to different value of delta, we can draw the Pareto frontier.
So this X is the model parameter,
It's this delta?
X.
Yeah, that's a model
I'm
parameter.
gonna go to the assumption that you still need a minus for the delta in the first
minus?
I think so, yes.
Mm, I don't think so. So if you add the absolute value here, and then you want the absolute value minus, because actually this probability, the first probability is equals 1 minus the second one. So if you move the 1 to the right-hand side, and flip the sign, okay. And corresponding to different value of the delta, we can draw the Pareto frontier. So for the Pareto frontier, the y-axis is the performance. Here is the AUC. And the x-axis represents the level of fairness. So if delta gets smaller, it means that this model is more fair. And the Pareto frontier means that under the same level of performance, the Pareto frontier represents the model with the greatest level of fairness. And under the same level of fairness, Pareto efficiency frontier represents the model with the best performance. Okay. So let's first look at the objective. We want to maximize AUC. By definition, we want to maximize this conditional probability, and we can write it as minimize this probability with flip sign. Okay. And it's equivalent to minimize the expectation of the indicator functions. But the indicator function is discontinuous, so normally we will replace it with a continuous surrogate loss. So here we replace it with a quadratic loss. However, if we look at this formulation is generally computationally challenging because the expectation is taking over a pair of random data points, one from the positive group and the other from the negative group. So if we formulate it with the empirical distribution with n data points, the computational cost would be quadratic in data size. And also it's not suitable for online learning. Here, the online learning means that the data comes in sequentially, and we need to update the model by the latest data. So here, if we want to, it is not suitable for online learning because we need to compute the stochastic gradient. So we need the data to come in pairs. However, it cannot be guaranteed in practice. So that's why it's not suitable for online learning.
Is it possible to collect 2 pairs of data in sequence and then run it?
But you don't know, I mean, when the data will come in, I mean, for the online learning. Yeah. Okay. And
Give us a scenario in which you would deploy something like this in online learning.
you mean for online learning? What do you mean?
What is this? This is like
prisoners
or granting loans or
Banking.
banking, fine, whatever, yeah. Granting loans, banking is online. Is this suitable for online learning?
For example, in application for like the bank or some like places, you need to update the model by the latest data set.
If every bank is a local.
Online, what you are saying here is not the latest data set. You are saying here is that the latest data.
You mean the exactly the latest?
Yeah, because
no, I mean really the question I'm asking is that, let's say somebody came in, I gave him a loan, he defaulted on the loan. Right away, I'm going to go and change my model.
it's like, what is even the motivation
That's
to
what
look for online learning? Why can't just collect the data and learn it, right?
Right.
Like, we are not going to update the model every instant somebody is coming. So
Yes,
what is the motivation for online learning? We might not even need it. So
But it's still the computational cost is quadratic, right? So
yeah.
that's- And maybe let's go with that.
So based on in 2016, the expectation of the loss can be written as the optimal value of a min-max optimization. So the previously we want to minimize this expected loss, it can be written as a min-max formulation. Okay. So with this min-max formulation, we can see that we only have the expectation taking over one random data point. So it's suitable for online learning, and the computational cost is only linear in data size. And similarly, for the two constraints, we can also write them into this min-max formulation. So this problem becomes a min-max optimization with min-max constraints. So here, for simplicity, I use a bold X to represent all primal variables. So it becomes this formulation. And however, the challenging is that it's a new structure, it's a min-max optimization problem subject to min-max constraints, and it involves both max and expectation. So the gradient of the F is not easy to compute. To solve this problem, we use a level set method. So before we use it, we need to first have the level set function, which is defined as minimize the PRX, and the PRX is defined as max the F0 minus R, F1, and F2. And here R is called the level parameter. So if we want to use a level set method, we need some assumption. So first, we need to assume strict feasibility and also the convexity and the bounded gradient. So then under the strict feasibility assumption, we can see that this level set function is a non-increasing and convex in the level set parameter R. So actually it becomes a root finding method because the R equals F star is a unique root for this level set function equals 0. Okay. So let's look at the level set method. So the level set method generates a sequence of R convergent to the F star by a root finding scheme. And to update the R, we need this oracle, this stochastic oracle that satisfies these two inequalities. Actually, this oracle can be the algorithm for the level set subproblem. The level set subproblem is minimize the PRX. Okay. So I will use the graph to show the level set method. So suppose we start from the RK, and at this RK, we can compute the upper bound of the level set function, the U at RK. And then we update the R by RK plus U at RK. So since the U, the upper bound is negative, so which means that we move to the left-hand side of the R. And similar for RK plus 2. So actually we get closer and closer to the F star. So here, the solution, the root here. So if the RK minus F star smaller than epsilon, XK is feasible and the epsilon optimal solution. And then, as I said before, we need the stochastic oracle. So it should be the, it can be the algorithm that solve the level set subproblem. So
what do you mean by stochastic oracle? Like oracles need to inspire some trust. When you use stochastic, that does not really inspire trust. So what is a stochastic oracle?
Stochastic means that for each iteration, you don't need to go through the whole data set. Yeah, you just pick the sample and then just do the gradient.
Yeah, but that is fine. I have another question adjacent to it. The consideration of this bounded gradient, uniformly bounded gradient, you consider, right?
Expectation.
Yeah. So that's a very strong condition. That one. The last one. That is
this one?
Yeah, that's a very strong condition. No?
No, I think it's normal for stochastic oracle. Like
I disagree, but like anyway, so
what?
let's move on. Yeah.
Okay, I think like every stochastic algorithm, they need to have this bounded. I mean, bounded
It
like
should
very
be somehow bounded with respect to a reference point for that gradient. So you can consider the variance of that gradient.
Oh, okay.
Iterate from some
Okay, I see.
reference point
You mean the
that is
variance?
bounded.
Yeah.
So you see, so the gradient will be some constant plus something that is varying with the iteration. So that should be a easier,
Okay.
weaker condition. So
Oh, yeah.
this one is saying everything is lying within a uniform ball, which is very, very strong condition. And
Yeah.
I would not,
Uh,
yeah, but anyway, so let's move on.
Yeah, I will check that.
Yeah.
Yeah, I agree, yeah. So normally we just assume the variance bounded, right?
Mhm,
Yeah.
mhm, yeah.
Okay, so let's look at the algorithm that can solve this sub-problem. So the corresponding sub-problem is that we want to minimize the PRX, okay? And it's equivalent to max F0 minus R, F1 and F2. So we can introduce the dual variable belong to the simplex. So it becomes a min-max formulation. And here replace the F0, F1, and F2 with the definition, we can get this min-max formulation. So we want to minimize over X, max over Y and alpha. So since here, observe here, we have, the joint term of Y and alpha, and if we compute the Hessian, we can see that actually this formulation is not jointly concave in Y and alpha. So the standard stochastic gradient descent cannot be applied here. May not converge here.
Can you tell me which is the final classifier after this optimization?
The what?
The finally after you've trained, which is the classifier, the pair classifier
Yes.
in this equation and in this problem?
The
Final classifier.
the final classifier?
Is that the X, the model, the final?
Oh, yeah, it is a X,
X.
the model parameter.
And where is the sensitive attributes now in the Z?
The sensitive attribute is Z has the label, the feature vector, and the sensitive variable.
I have one more question. So in this, so you've shown one protected, one sensitive attribute, right? How general is this method? Like if you have two sensitive attributes, how general is this approach? Is it can be extended to two or multiple sensitive attributes or?
So it's depend on how you, define the fairness if you have several sensitive variables. Yeah, because if you have several sensitive variables and then you have the output of the model, so how should we define the fairness? That is the first problem. Yeah, so how? I'm not sure, so.
So Z can be a vector, for example. Z you
Can
must
be.
have a vector of attributes.
Yeah, it's included the feature vector in Z.
But you consider only one sensitive attribute in this approach, right?
So right now we only consider one sensitive variable, but I think it should be possible, but the first problem we need to know is that how should we define the fairness if we have several sensitive variables? So we want to consider the joint distribution of the score or something.
Sensitive attribute is what? Is
Is-
protected versus not protected? What is the sensitivity in this one right now? You have one, right?
No, the sensitive variable, it can be protected or unprotected.
So for example.
It's for example, if it's black or white, so if we say black is 1 and the white should be -1, it's like that.
Okay,
So when you protect,
So-
when is unprotected.
so one is a race, right? That's like a race,
Mhm.
but you can have also gender can be another attribute.
Yes,
So that's what they're saying.
yeah.
Gender,
Yes,
race,
yes.
age.
Yes,
But in
But-
this
but
case, you
sometimes-
cannot consider both together, right? You considering.
we consider only one, but the problem is that sometimes you need to first investigate the data set. For example, like you should first check that the data set is like, for example, I have the data set, it's quite fair, like corresponding to gender, but it's maybe like unfair for race, so it depends on the data. Yeah.
Okay.
Thank you. So it may not converge. So we let alpha tilde equals y times alpha, and we replace the y and alpha with y and the alpha tilde, and we get the perspective function of this formulation. So this perspective function, which is jointly concave in y and alpha tilde. Okay. So then we use the stochastic mirror descent. We first do the stochastic gradient descent for the x, and then we do the gradient descent for the dual variables. So here we are not using the L2 norm because it may need another oracle to solve it. So we introduce spatial divergence. So this spatial divergence can allow a closed form update for this y and alpha tilde. So you don't need an oracle to solve this formulation. So this is a convergence theory. So if with the upper bound defined as this formulation and the stochastic mirror descent has this output, we can show that this stochastic mirror descent is a stochastic oracle of the level set function, and we can find the feasible and epsilon optimal solution after this kind of iterations.
But how is this epsilon optimal solution defined for this problem?
It's get closer to the optimal value.
It's
Global optimum.
Distance.
Yeah.
From that point.
No, it is like global optimum.
Yeah, it's global. It's global optimum. So this is a optimal solution.
It's non-concave problem, right?
Sorry.
Problem was non-convex, right?
No, it's a convex.
It's right now. Yes, we assume convex. Yeah.
She transformed it, but go through the theorem, please.
So the transform due to level sets, it becomes.
Right. So you are taking the output as the average of all the iterations? Like the X bar.
X bar.
X bar.
Oh, yeah.
So that means you have to have the copies of all of these in your memory.
But you can update it
Yeah,
after you
but
get
but
X.
but can you not take just like the last one? Can you say like the last iteration? Because this is a nice function.
I mean,
I don't think so because
the previous.
No, I agree with that. I agree with that. Sorry, that's a bad question, bad comment. But you can always do the last iterative convergence here, right?
But
It's a concave function. You can say even the last, so what is the point of running the iterates?
but I mean in the theory we normally need the weighted average. Like you cannot show that, like if you show the convergence theory, you cannot show the convergence with the last iteration.
Standard stuff, the mirror distant convergence.
Yeah.
Instead of the
But for
average.
nice function, it can be done for the last iterate as well. But anyway,
Yeah, they're just one step away from this. I think it is easier to do.
right?
I know it's easier to do, but I
Yeah.
mean, in proof, you cannot show that. I mean,
Yeah, you will love this place. There's so many people.
yeah, sure.
Very good.
Yeah, this is the numerical results. We have 3 data sets, adult, bank, and compass. And for the adult, the sensitive variable is male or female. And for the bank, the sensitive variable is age. And for compass, the sensitive variable is the race. So we train for the linear model and the 2-layer neural network. We compare with these 3 benchmarks. The first one is proxy Lagrangian. It's a Lagrangian method use indicator functions, and the post-processing, it shifts, do the linear shift for the score if the sensitive group is a protected group. And the third benchmark is correlation penalty. It penalizes the correlation between the score and the sensitive variable. Okay. So this is our numerical results. It's draw the parallel frontiers of the benchmarks for different data sets. So here the y-axis is the performance, which is the AUC. It should be as large as possible. And the x-axis represents the fairness. So if the value in the x-axis gets smaller, it means that this model is more fair. And for the parallel frontiers, we want that this curve to be as up as possible. So the upper, the better. Okay.
So is this within noise?
No.
I mean, like the differences are between like on the first one, the difference is with 0.8885 versus 0.88, and some of the differences are at the third, are kind of at the third number.
Yeah, because it's a stochastic, I mean,
I know, I understand that one, but still your data set was like around 10,000. And with 10,000 pieces of training data to get the difference, which is like in the, only shows up on the, at your fourth significant number, right? You would say that, hey, any difference between 0.88, does that, how many actual people are going to be released?
Benefited from this, like how much difference it will make practically for this data
So
set?
you have a data set of 10,000, right?
yes,
Okay, you are using, I don't know, the level set versus the, which one is the dotted one, the
yeah,
post-processing, right?
Proxy.
yes.
Okay, and is there anybody actually, let's say this is the prison parole thing, is there even one person who is going to be differently released with the difference?
These results
you
are very
say
close
that,
what you
yeah.
have.
Yes,
Compared to
yes.
the method, the level set and proxy is very, very close.
Yeah, so this, yeah, sometimes they are close, but for a, like, for example, for the bank data, the proxy Lagrange has, I mean, the much worse performance.
Okay, well, let's go that one is simple, so even that one is at the, even that one is,
So it's close to correlation.
quite close, right? So the question is, can you explain, is this statistically significant, the difference? Because maybe you had a, you know what I'm saying?
But here, the
Yes.
third one here, so she had a better one, third one.
But the y-axis is.
Yeah, well-
Y-axis is very expanded.
Oh, I see.
Yeah.
Even that one is, that one is.
Yeah, because the scale.
Yeah, yeah, so here, I first want to say is that, here we have the small bar here, it means I run several times with different random seed, it's represent the standard deviation. So, and as, so you said for the statistic, we don't have like a statistical,
I don't know, hear about p-hacking,
no.
anybody heard about p-hacking?
Yes, yes, sure.
Well-
But here on the A9A, for example, they don't seem to be statistically different, but for example, in the compass data set, they are.
But look at the scale of the compass data
Yes,
set,
but
it's
look at the-
7.34 to 7.4.
But these are box plots, these shapes. Like they are showing the deviation. And you
Yeah,
see-
but like standard
Okay, fine,
deviation
that's-
0.01.
Okay, we can.
Yeah, that's
discuss
fine.
it further, right?
Yeah, but I also want to say that, like, obviously the post processing is the fastest one because you already achieved the model, you just need to shift it. But sometimes the post processing cannot be applied. I mean, it cannot be applied to some kind of fairness metrics. And among the level set proxy Lagrange and the correlation, the level set is the fastest, faster than the proxy Lagrange and the correlation, because they need the pair of data.
The one advantage of level set, which I can see, is it is agnostic to the data set where you apply, it is consistently better, while others are depending upon the data set changing the performance. So that's, it means it is somehow capturing some statistical properties of
Yeah,
the data which others are not.
Yeah.
Yeah.
That's one.
It's consistently good.
It's consistently good.
That's good, yeah.
So, and my methods, my work can extend to the fairness of multi-output model. So for the multi-output model, similarly, we have Z equals Kc S represent the random variable, and Kc is the feature vector. So here the S, I use 1 and a -1, represents the protected and unprotected group. So the multi-output prediction model, which means that the output of the model has more than one dimension. Okay. So the multi-output model has several applications, for example, multi-class, multi-label, multi-task, prediction, and the embedding of representation learning. Okay. So how should we measure the fairness of the multi-output model? So previously, as I said, if the output of the model is only one dimensional, we can simply draw the distribution and see if there is any difference. However, this only works for one dimension. how about if the dimension is like more than 1? So let's see if the dimension is 2. So we plot so it's just I mean, an example. So it's the distribution of the output of the model and for different sensitive group. So the sensitive group is every married or not. And for the graph on the left, we can see that the point for the two sensitive group mixed together. We cannot simply use a line to separate them. So we call this model is fair. And for the graph on the right, we can simply use a green line to separate the sensitive group. So we call this unfair. Okay. So which means that we want to use a linear model Y to classify the sensitive variable based on the output of the model. Okay. So the ideal case is that we cannot use any linear model to classify the sensitive variable. So previously, if we use if in traditional machine learning, in the objective, we want the loss to be as small as possible. However, if here we consider it as constraint, which means that we use the linear model to predict the sensitive variable. We want the expected loss to be as large as possible.
Here I have a question. You don't go back to the two class problems. You compare protected and unprotected one by taking the difference on the distributions.
Yeah.
The taking average. Why are you choosing that as the measurement of the fairness? When you compare two distributions, why you think the difference of the two distributions can reflect the intel situation?
Because if you look at this, it's the output of the model. It's the output of the model, which means that
the H are two distributions, right? Protected and unprotected groups.
actually it's like 1 because the output is only 1. Yeah,
Yes.
Here the
previous
H.
slide, you're comparing two distributions, right? You're taking the difference.
Oh yeah,
in your
yeah. This distribution means the output of the model for the two.
Yeah, but why are you taking the linear comparison? Why are you taking the difference to see two cases? Why are you not taking the ratio? Or like when comparing some statistical common graph graph test, you are taking the difference but taking the maximum, not the average. Why are you using that as the measurements?
You mean for the one-dimensional output model?
Yes.
Because if their density curve can, overlap, which means that, the output of the model is like independent of the sensitive group.
See, I can create the easy case. One distribution is flat, uniform. Another is bell curve. When I average them, the difference is 0. Then
Why we take average?
Because I have expectation on there.
But it's different. It's here is not about the.
In your two cases, you have an expectation, but the expectation is with respect to the Cassie or with respect to what?
It's different because actually this method is like how to say that? So the ideal case, we want to look at the difference of the distribution, right?
Yeah, so do you use scale divergence or something?
No, so it's my future work. I plan to use the Wasserstein distance.
Yeah.
So like my previous work is just to talk about like a small step forward, which is weaker than the difference of the distribution,
Right.
not exact the distribution.
Yeah, if you don't take the difference between two H functions, you change into, for example, likelihood ratio, it's a ratio, or Watson distance, you still rewrite the Intel problem into the framework, optimization framework.
If you take the Wasserstein distance, it's I don't think it can fit its framework. It's need a new framework. Yeah. But that for AUC is just like a small step because it's weaker than the Wasserstein distance. But my future step will consider the Wasserstein distance. Yes. Okay. Okay, so
We have only 10 minutes left because you have another meeting, so
okay.
maybe try to.
Yeah, sure.
Mhm.
So here, so as I said, if we want to use it as the constraint, we want the expected loss to be as large as possible. So how large we introduce a kappa, so it can control the level of fairness. And here the L is the loss function. Okay, so actually it becomes, we want to minimize fx subject to the gxy smaller than 0 for any y belong to the capital Y. So here capital Y is a set. So which means that we have infinitely many constraints. So this is called a semi-infinite programming. So semi-infinite programming can be applied to robot trajectory design and statistics and kernel learning and also robust optimization. There are some existing methods that can deal with the semi-infinite programming. For example, discretization method, cutting plan method, reduction method, and exchange method. However, these methods are all deterministic. So which means that they are not good for large data set. And they may have the curse of dimensionality. For example, if we use a discretization method, we sample finite many y to approximate the infinite many y. So which means that if the dimension of the y increase dramatically, the number of samples need to be increased dramatically. Okay, so we propose a new algorithm. First, we need assumption, the convexity and the compactness, and also the smoothness and the Lipschitz continuity. So here we define a epsilon optimal solution if it satisfies these two inequalities. So recall that it is our problem, and we can introduce a Lagrangian multiplier lambda, and we can get phi. And since this phi is not jointly concave in lambda and y, but it's concave in y fixed, it's concave in y fixed lambda and concave in lambda fixed y. So we can sequentially update the y and the lambda, and then we update the x. However, this is not fast enough, so we introduce the historical change of the gradient to the previous gradient. So it called the momentum term. So it can, accelerate the previous algorithm. So it's a theory. So if F strongly convex and G strongly concave, we can achieve the epsilon optimal solution after big O 1 over square root epsilon iterations. And otherwise, the complexity is big O 1 over epsilon. We can also develop the stochastic case. Suppose we have unbiased and variance bounded stochastic oracle, and we should have the convergence rate to be big O 1 over epsilon squared. So let's look at the experiments. So first, we consider a multi-class classification. We want to predict the label, which can be 1 to capital C, and we want to minimize the expected cross-entry loss subject to fairness constraints satisfied. Okay. And we consider this customer segmentation. There are 4 customer categories, and the sensitive feature is marital status. And we compare with 2 baselines, the SIP Comiro method and the smoothing penalty method. And this table shows a convergence rate for the baseline. So here we can see that under the convex case, actually we have like improved convergence rate. And also when we have strongly convex, we also have improved convergence rate. So this is a convergence result. Because here we use the since we have like about 6,000 data, so here we conduct it deterministically. So there is not too much difference, but still we can see that our method AGSIP converges faster than the baselines. So the left is the objective value against the CPU time. The right is a constraint violation against the CPU time. And this is the performance. So it's plot the output of the model and projected it to 2D space with the TSNE. And the left-hand side is without fairness. We can see that we can use a red line to separate. And the right graph, we can see that we can the two kind of dots are mixed, so we cannot separate them. The right graph is after we enforcing the fairness. And let's look at another experiment, the multi-label classification.
So on this one, did you have actually numbers, like
Mhm.
your method compared to other methods? How good it is, like how much?
You mean,
It converges faster, which is good, but how about accuracy of your method? Like
Accuracy.
you are comparing in other
mhm.
methods, you show area under curves, right?
We do not consider the test performance,
The
which is,
classification accuracy is compromised, that's been.
yeah, sure.
It's just,
You-
accuracy is not good, but its converges faster, is that what you're saying?
You mean compare with baseline?
Yeah, I mean, see the existing methods,
We,
but your method which is faster, but how good is it?
we do not compare the test performance
But I mean, why do you need your method then?
because it converges faster.
I mean, if it doesn't do better than.
Yeah,
other
but-
methods, then so you need to-
But I mean,
That's fairness.
but I believe it should be better, yeah.
Also, if you run this one after 40 seconds, if you
Yeah.
run it to 60, will the red line be below the blue?
No,
Guaranteed?
yeah, because I run it.
But also, what's the meaning of not being able to separate it with a linear classifier? I mean, you could separate them maybe in a higher dimensional space. Why is this really capturing?
No,
I
I,
understand.
it's in high dimensional space. What do you mean? You mean why consider the linear classifier?
Yeah, I mean, as a measure of fairness, you essentially don't want to be able to classify based on this.
yeah,
this
yeah,
aspect.
yeah.
So you're trying really to increase the entropy of your data in a way. But you might be able to separate this data in some higher dimensional space. So why is this really capturing?
But I mean, in high space,
That's
yeah,
more fair.
but I mean, here I just use the example, the two-dimensional example, just want you to see it clear, but in high space, it's also like,
What I meant is that you can take the two-dimensional data and use a kernel to push it to higher dimensional space, and then you can find a separating hyperplane. The kernel methods do that, even if the data is two-dimensional. So you can have a
Okay.
nonlinear separator, but in a higher dimensional space, it will be linear by just applying some.
Kernel.
it's like a cutting plane method.
No, it's
a kernel, it's a kernel.
It's a
Like-
kernel.
Oh, okay.
Just a mapping from this space to and then classify in that space.
So in that case, the data will still be linearly separable, but in a higher dimensional space as opposed to in the original feature space.
No.
So you define,
But I
new
mean-
features, you define new features. So this is
Oh, okay,
It's a transformation.
okay,
And
okay,
after you
okay,
apply the
I see.
transformation, the data becomes separable. So why is this really capturing fairness? In my mind, it's.
So after, you mean you lift it to like high space?
Yes, yes. And then
Okay.
you can separate the data there.
Okay, but is it still fair or not?
No, so what I'm saying is
Well,
that this
there is no
doesn't.
such thing as fair, right? You are,
Life is
the
unfair.
point here is that.
Okay, so you consider it's fair, but if you lift it to the high space,
You
it
can say-
becomes unfair.
Yeah. And anyway, I want you to finish your slides and then we can talk more because I have a few slides left.
Yeah.
Yeah, just want to show here, I think we should have the best, the better performance. So here, okay. So this is a multi-label classification and we use the like the syllable A, it has more than like 200 how many? To 200,000 face images. And here, since we have many images, so we use the stochastic version. So if we use stochastic version, we can see that we converges much faster.
Yeah, so Subcell Bay is pretty famous data set. So from the practical point of view, I'm interested to see how does it compare with
Mhm.
other methods and performance.
Okay,
No, its coverage is very good, that's fine, but.
yeah,
that
yeah,
should,
sure.
yeah.
So because previously, the contribution of our work is that we show like a good complexity, so we just compare the convergence rate.
Thank you.
Convergence rate.
One more slide.
Yeah, no, it's just about, this talk is related to these two works, but I have another work is like deal with the difference of convex programming. So if you are interested, you can look at.
So, I mean, it's just the measures of fairness are a little bit questionable. I've seen work, for example, where people use information theoretic methods in which, for example, one clear idea, if you condition on the data, you want to make sure that the labels do not tell you anything about the features. So you try to minimize the visual information. Hence, you minimize the information leakage about the sensitive attributes. That seems to be like a more natural metric of what fair would mean. Than the metric of being able to separate the data with a linear classifier or not. So I think you need to show us that what you're doing is more fair, in a way. Why is it fair? You're showing the same metric that you try to optimize. Sure, you're not violating the constraint.
Okay.
But then why is that really more fair?
But I mean, you cannot say it. I mean, it's more fair because it's depend on how you define the fair.
Yes, and the more natural definition would be that you cannot leak information about the sensitive attributes, given that I give you the labels of the data and I condition on the data labels, for example. That would be a clear measure of.
Yeah, so I think
that
that
is with real data, and you can probably avoid unjust classification of this many users. So you can do back testing with real data.
yeah, so you'll have time to talk to the search committee. I
Okay.
think it's now lunch, but it's a very nice talk. I really like it.
you.
This topic of fairness is very, very crucial, very
Yeah.
important. So you're doing, working on a very good topic. And I think you've answered question pretty well. So thank you.
Thank you.
I think you can get,